Beyond the blue sky of our days and the dark nights above us, something unseen is always in motion. Powerful forces move through the air, shaping the world we live in. Above our heads lies a thin layer of atmosphere, a fragile shield that makes life on Earth possible. Within this layer, energy from the sun drives a constant cycle of movement. Air warms and rises, winds travel across continents and oceans, water evaporates, forms clouds and falls again as rain. Together, these processes create the weather we experience every day and help regulate the planet's climate. This is a system both delicate and powerful, a global engine powered by sunlight, air, and water. By understanding how it works, we begin to see the hidden connections that sustain life on Earth. But as we uncover the forces shaping our planet, one question remains. If such complex systems quietly support life every moment, how much of the world around us are we still learning to truly notice? The thin gaseous envelope cradling our planet, often compared to the merest varnish on a classroom globe, is not a uniform blanket, but a series of distinct layers, each playing a critical role in the grand ballet of weather. Closest to the surface, where all life unfolds, lies the troposphere, a dynamic realm extending roughly 8 to 15 kilometers high, depending on latitude and season. This is the very engine room of weather, where clouds form, winds stir, and all the phenomena we perceive as daily atmospheric conditions manifest. Above it, the stratosphere stretches upward, a more serene region where air flows predominantly horizontally, home to the vital ozone layer that shields us from the sun's most harmful ultraviolet radiation. Higher still, the mesosphere and thermosphere fade into the vacuum of space, each with decreasing density and distinct thermal characteristics. Yet all are intricately connected, forming a single vast system. Energy from the sun, the ultimate driver of this system, enters our atmosphere and is distributed through fundamental principles of heat transfer. Conduction, the direct molecular transfer of heat, warms the lowermost layers of air as it makes contact with the heated Earth's surface. Convection then takes over, as warmer, less dense air rises, carrying its thermal energy aloft, only to cool, condense, and eventually sink, creating vast circulatory currents. Radiation, the transfer of energy through electromagnetic waves, is how the sun's energy reaches us in the first place, and how the Earth radiates heat back into space. This constant dance of energy absorption, transfer, and emission dictates global temperatures and fuels atmospheric motion. Central to all weather is the ceaseless journey of water. The water cycle, a process as ancient as the Earth itself. Solar energy evaporates water from oceans, lakes, and rivers, transforming it into an invisible gas called water vapor. This vapor ascends into the atmosphere, cools and condenses into microscopic droplets or ice crystals, forming clouds. When these droplets grow heavy enough, they fall back to Earth as precipitation, replenishing our water sources and completing the cycle. This continuous exchange of water between the Earth's surface and the atmosphere is not merely a passive process. It releases latent heat during condensation, a powerful energy source that drives many weather systems, particularly intense storms. On a grander scale, the Earth's rotation and uneven solar heating create vast global air circulation patterns. Near the equator, intense solar radiation causes air to warm and rise, creating a zone of low pressure. This rising air flows poleward at high altitudes, cools, and sinks around 30 degrees latitude, forming subtropical high-pressure zones. These movements establish the Hadley cells, driving the trade winds that have historically propelled sailing ships across oceans. Further poleward, the ferrule cells and polar cells continue this atmospheric conveyor belt, creating prevailing westerlies in the mid-latitudes and polar easterlies. These immense circulation patterns are not merely theoretical constructs, they dictate the broad strokes of climate zones and the general direction of weather systems across continents. Finally, the intricate interplay of temperature, pressure, and humidity governs the immediate conditions we experience. Temperature, a measure of molecular kinetic energy, directly influences air density. Warmer air is less dense and tends to rise, while cooler air is denser and sinks. This density difference creates variations in atmospheric pressure, the weight of the air above a given point. High-pressure systems typically bring clear skies and stable conditions as air descends, while low-pressure systems are associated with rising air, cloud formation, and precipitation. Humidity, the amount of water vapor in the air, influences how readily clouds form and how much latent heat is available to fuel weather phenomena. These three fundamental properties are inextricably linked, each influencing the others in a continuous, dynamic feedback loop that defines the very essence of weather. Air pressure, The invisible weight of the atmosphere pressing down on every surface is a fundamental force shaping our weather. High-pressure systems are characterized by descending air, which warms as it sinks, leading to stable atmospheric conditions. This descending air suppresses cloud formation, resulting in clear skies, calm winds, and often fair weather. Conversely, low-pressure systems are regions where air is rising. As this air ascends, it cools and expands, leading to the condensation of water vapor, the formation of clouds, and an increased likelihood of precipitation and stormy weather. The contrast between these systems, the difference in their atmospheric weight, is what sets the stage for much of our daily weather experience. The movement of air from areas of high pressure to areas of low pressure creates wind. The atmosphere's attempt to equalize pressure differences. The greater the pressure difference over a given distance, known as the pressure gradient, the stronger the winds will be. This constant striving for equilibrium is the primary driver of all atmospheric motion. Furthermore, the convergence of air into a low-pressure system and its subsequent upward motion acts as a lifting mechanism that can initiate and intensify storm formation. The very rotation of hurricanes and tornadoes is a direct consequence of air spiraling inward towards an incredibly intense low-pressure center, driven by these powerful pressure gradients. Atmospheric pressure is not uniform across all altitudes. It dramatically decreases as one ascends. At sea level, the average atmospheric pressure is around 1,013.25 millibars, but for every 100 meters gained, the pressure drops by approximately 12 millibars. This is because there is simply less air pressing down from above. This relationship between altitude and pressure is crucial for understanding why mountain climbers experience thinner air, or why airplanes need pressurized cabins. The density of air, and thus its pressure, is a direct consequence of the amount of air molecules present in a given volume, which diminishes significantly with height. Pressure gradients, the rate at which pressure changes horizontally across the Earth's surface, are the invisible architects of local weather. A steep pressure gradient, where pressure changes rapidly over a short distance, indicates strong winds and potentially turbulent conditions. Conversely, a gentle pressure gradient suggests weaker winds and more stable weather. Meteorologists carefully map these gradients using isobar lines on weather charts, lines connecting points of equal pressure, to visualize wind direction and strength. The closer the isobars, the stronger the winds, providing an immediate visual cue to impending atmospheric dynamics. Understanding barometric pressure readings is a cornerstone of weather forecasting. A rising barometer, indicating increasing atmospheric pressure, generally forecasts improving weather and clear skies, as a high-pressure system is moving in. A falling barometer, on the other hand, signals decreasing pressure, often portending the arrival of a low-pressure system, bringing with it clouds, precipitation, and potentially stormy conditions. The rate of change in barometric pressure can be as important as the absolute value. A rapid drop often precedes severe weather. These readings, when combined with other meteorological data, allow forecasters to paint a comprehensive picture of the atmosphere's immediate future, offering crucial insights into what the sky holds in store. The transformation of invisible water vapor into the ethereal beauty of clouds is a delicate dance of thermodynamics and atmospheric conditions. It begins with the ascent of moist air, which, as it rises, expands and cools. This cooling is critical because cooler air can hold less water vapor than warmer air. Eventually, the air reaches its dew point, the temperature at which it becomes saturated with water vapor. At this precise moment, if tiny airborne particles, microscopic dust, pollen, or sea salt are present, the water vapor condenses around them, forming minuscule liquid water droplets or ice crystals. These myriad droplets, too small to fall individually, become visible as a cloud. This process releases latent heat, further influencing the surrounding atmosphere. Clouds are not a monolithic entity. They are classified into distinct types based on their appearance, altitude, and the weather they typically bring. High clouds, like the wispy cirrus, feathery cirrocumulus, and veil-like cirrostratus, are composed almost entirely of ice crystals and reside above 6,000 meters, often signaling fair weather or the distant approach of a warm front. Mid-level clouds, found between 2,000 and 6,000 meters, include altocumulus, appearing as patchy white or grey layers, and altostratus, a greyish sheet that can obscure the sun. Low clouds, below 2,000 meters, encompass the featureless stratus that often brings drizzle, the lumpy stratocumulus, and the fog-like nimbostratus, which produces continuous rain or snow. Observing cloud types offers a subtle yet powerful indication of upcoming weather changes. The movement of cirrus clouds from west to east can often be an early sign of an approaching warm front and its associated precipitation. The sudden appearance of towering cumulus clouds with their flat bases and cauliflower tops suggests instability in the atmosphere and the potential for afternoon thunderstorms. A darkening, thickening layer of altostratus evolving into nimbostratus is a clear harbinger of extended periods of rain or snow. These visual cues, honed by centuries of observation, provide immediate, on-the-ground meteorological insights. Beyond their aesthetic appeal and role as weather indicators, clouds play a vital role in regulating Earth's temperature. By reflecting a significant portion of incoming solar radiation back into space, particularly bright white clouds, they exert a cooling effect on the planet. Conversely, clouds also trap outgoing long-wave radiation emitted by the Earth's surface, acting like a blanket and preventing some heat from escaping, especially at night. This dual role, both reflecting sunlight and trapping heat, creates a complex feedback mechanism that influences global climate and local temperature fluctuations. The balance between these effects is crucial for maintaining Earth's thermal equilibrium. The ultimate fate of many clouds is to produce precipitation, a process that begins when cloud droplets or ice crystals grow sufficiently large to overcome atmospheric lift. In warm clouds, collision coalescence is the dominant mechanism. Larger droplets collide with smaller ones, merging and growing until they are heavy enough to fall as rain. In cold clouds, the Bergeron process is key. Ice crystals grow at the expense of supercooled water droplets, which evaporate and then deposit onto the ice crystals. These growing ice crystals can then fall as snow or melt into rain as they descend through warmer air, or even become sleet or hail depending on the temperature profile of the atmosphere below the cloud. Each cloud type, with its specific temperature and moisture characteristics, contributes uniquely to the planet's hydrological cycle. The invisible currents of air that sweep across our planet are not random gusts, but rather the result of fundamental physical laws, primarily influenced by the Earth's rotation. This rotational effect, known as the Coriolis effect, deflects moving objects, including air and ocean currents, to the right in the northern hemisphere and to the left in the southern hemisphere. It doesn't initiate movement, but modifies its direction, transforming straightforward pressure gradient-driven flow into complex curving wind patterns. This force is negligible over small distances, but becomes profoundly significant over the vast scales of global atmospheric circulation, shaping everything from trade winds to the spiraling motion of hurricanes. On a planetary scale, this interplay of solar heating and the Coriolis effect establishes the Earth's global wind patterns. The persistent easterly trade winds blowing from the subtropics towards the equator were historically crucial for sailing vessels. In the mid-latitudes, the prevailing westerlies dominate, carrying weather systems across continents. High above, narrow bands of extremely fast-moving air, known as jet streams, snake around the globe, acting as atmospheric highways. The polar jet stream, found at the boundary between cold polar air and warmer mid-latitude air, significantly influences the path of storms and cold air outbreaks, directly impacting the weather we experience daily. Beyond these grand global currents, local wind phenomena add intricate detail to the atmospheric tapestry. Sea breezes, driven by the differential heating of land and water, develop during the day as warmer air over land rises, drawing cooler air from the sea inland. At night, the process reverses, creating a land breeze as the land cools faster than the water. Mountain winds, orographic effects include anabatic winds that blow up slopes during the day as the sun heats the mountain sides, and katabatic winds that flow down slopes at night, carrying cold, dense air into valleys. These localized circulations demonstrate how terrain can profoundly influence atmospheric behavior on a smaller scale. The relentless movement of these wind patterns plays a pivotal role in shaping the Earth's diverse climate zones. The trade winds, by constantly pushing warm, moist air towards the equator, contribute to the heavy rainfall and lush vegetation of tropical rainforests. The prevailing westerlies, carrying moisture from the oceans inland, are responsible for the temperate climates and seasonal precipitation of many mid-latitude regions. Conversely, the descending air associated with subtropical high-pressure zones, where winds are generally light, creates the arid conditions characteristic of the world's great deserts. Wind is not merely a consequence of climate, it is an active participant in its creation and maintenance. The physical landscape, with its mountains, valleys, and vast plains, exerts a powerful influence on wind behavior. Mountains act as formidable barriers, forcing air to rise and creating orographic lift, which often leads to precipitation on the windward side and a rain shadow, a dry area on the leeward side. Valleys can channel winds, intensifying their speed, while large bodies of water can moderate temperatures and influence local wind patterns. The friction between the moving air and the Earth's surface also slows winds near the ground, creating turbulence and varying wind speeds at different altitudes. This complex interaction between atmospheric dynamics and geographical features ensures that no two locations experience wind in precisely the same way. The atmosphere, typically a realm of gentle breezes and soft clouds, can unleash formidable power in the form of storms, each a unique manifestation of intense energy release. Thunderstorms, the most common severe weather phenomenon, begin with the rapid ascent of warm, moist air, often triggered by intense solar heating, frontal systems, or orographic lift over mountains. As this air rises and cools, water vapor condenses, releasing vast amounts of latent heat that fuels further ascent, creating towering cumulonimbus clouds. Within these colossal structures, updrafts and downdrafts create violent turbulence, leading to heavy rain, lightning, thunder, and sometimes hail and strong winds. The life cycle typically progresses through cumulus, mature and dissipating stages, each marked by distinct internal dynamics. Tropical cyclones, known as hurricanes in the Atlantic and typhoons in the Pacific, are colossal rotating storm systems that derive their immense energy from warm ocean waters. They begin as clusters of thunderstorms over tropical seas, where sea surface temperatures exceed 26.5 degrees Celsius. As warm, moist air rises, it creates a low-pressure center, drawing in surrounding air, which then spirals inward due to the Coriolis effect. This continuous feeding of warm, moist air and the release of latent heat in the eye wall, a ring of intense thunderstorms surrounding the calm eye, allows the storm to grow into a massive, destructive vortex characterized by extreme winds, torrential rainfall, and devastating storm surges. Tornadoes, perhaps the most violent and localized of all atmospheric phenomena, are rapidly rotating columns of air extending from the base of a cumulonimbus cloud to the ground. Their formation is not fully understood, but they typically arise from supercell thunderstorms, which possess a rotating updraft called a mesocyclone. Within this rotating updraft, if conditions are just right, strong wind shear, a capping inversion, and ample moisture, a narrower, more intensely rotating vortex can descend. The precise mechanics of how this rotation tightens and extends to the surface, often producing winds exceeding 300 miles per hour, remains an active area of scientific research, yet their destructive power is undeniable. Winter storms encompass a range of severe weather conditions characterized by freezing temperatures and significant precipitation in the form of snow, sleet, or freezing rain. Blizzards, a particularly dangerous type of winter storm, combine heavy snowfall with strong winds, typically exceeding 35 miles per hour, reducing visibility to near zero and creating treacherous conditions. These storms form when cold air masses meet warm, moist air, often along frontal boundaries, leading to widespread and prolonged precipitation that falls as snow due to sub-freezing temperatures throughout the atmospheric column. The accumulation of snow and ice can cause widespread power outages, travel disruptions, and pose significant risks to life and property. Lightning and thunder are the dramatic electrical manifestations of intense thunderstorms. Within a cumulonimbus cloud, collisions between ice crystals and supercooled water droplets create a separation of electrical charges, with positive charges accumulating at the top of the cloud and negative charges at the bottom. When this electrical potential difference becomes too great, a sudden discharge of electricity occurs, either within the cloud, between clouds, or between the cloud and the ground. This discharge is lightning, an incredibly hot and rapid burst of energy. The intense heat of the lightning channel causes the surrounding air to expand explosively, creating a shock wave that we perceive as thunder, its rumble echoing the raw power contained within the storm. The sun, our planet's ultimate energy source, continuously bathes Earth in solar radiation, a fundamental driver of all atmospheric processes and temperatures. This electromagnetic energy, primarily in the form of visible light, travels through space and penetrates our atmosphere. About 30% of this incoming radiation is immediately reflected back into space by clouds, ice, and the Earth's surface, a measure known as albedo. The remaining 70% is absorbed by the atmosphere, land, and oceans, warming our planet. This absorbed energy is not uniform. Equatorial regions receive far more intense direct sunlight than the poles, creating the foundational temperature gradients that drive global circulation. Once absorbed, this solar energy warms the Earth's surface, which then radiates some of that heat back towards space in the form of longer wavelength infrared radiation. However, certain gases in our atmosphere, notably water vapor, carbon dioxide, methane, and nitrous oxide, are particularly efficient at absorbing this outgoing infrared radiation. This phenomenon is known as the greenhouse effect. These greenhouse gases trap a portion of the radiated heat, preventing it from escaping directly into space thereby warming the lower atmosphere. Without this natural greenhouse effect, Earth's average temperature would be a frigid -18 degrees Celsius, making life as we know it impossible. It is this delicate balance of absorbed and trapped heat that maintains our planet's habitable warmth. Heat transfer within the atmosphere occurs through three primary methods: conduction, convection, and radiation. Conduction is the direct transfer of heat through molecular contact, primarily responsible for warming the lowest layer of air as it touches the heated ground. Convection involves the transfer of heat through the movement of fluids, in this case air. Warmer, less dense air rises, carrying heat upward, while cooler, denser air sinks, creating vast convective currents that distribute thermal energy both vertically and horizontally. Radiation, as mentioned, is the transfer of heat through electromagnetic waves, how solar energy reaches Earth, and how Earth emits heat back into space, playing a crucial role in the overall energy budget. Temperature variations are not merely a matter of latitude. They fluctuate significantly across different regions and seasons due to a complex interplay of factors. Proximity to large bodies of water moderates temperatures, making coastal areas generally milder than inland regions, which experience greater temperature extremes. Altitude also plays a role, with temperatures typically decreasing with increasing elevation. Seasonal variations arise from the Earth's axial tilt, which causes different parts of the planet to receive more direct sunlight at different times of the year, leading to the distinct patterns of summer, autumn, winter, and spring. Local topography, cloud cover, and vegetation also contribute to the intricate mosaic of temperatures across the globe. Ocean currents act as massive thermal conveyor belts, playing a profound role in regulating global temperature patterns. Warm ocean currents like the Gulf Stream transport heat from equatorial regions towards the poles, significantly moderating the climates of high-latitude coastal areas, making them much warmer than they would otherwise be. Conversely, cold ocean currents bring cooler water from polar regions towards the equator, cooling adjacent land masses. This continuous circulation of warm and cold water redistributes vast amounts of thermal energy across the planet, directly influencing atmospheric temperatures, precipitation patterns, and the very distribution of climate zones around the world. Precipitation, the ultimate delivery of atmospheric moisture back to Earth, manifests in various forms, each dependent on the temperature profile within the cloud and through the atmospheric column. Rain consists of liquid water droplets that have grown large enough to fall from clouds, typically forming in warmer clouds or as melted snow. Snow forms when water vapor condenses directly into ice crystals at temperatures below freezing, and these crystals aggregate to form snowflakes that fall through an atmosphere that remains below freezing all the way to the ground. Sleet, or ice pellets, occurs when raindrops fall through a layer of sub-freezing air near the surface, refreezing into tiny ice spheres before impact. Freezing rain is similar, but the raindrops freeze upon contact with surfaces that are at or below freezing, creating a dangerous glaze of ice. Hail, the most dramatic form, consists of layered ice balls formed within strong thunderstorms, growing as they are repeatedly carried aloft and fall through different temperature regimes within the cloud's powerful updrafts and downdrafts. The formation of precipitation within clouds is a process of growth and accumulation. In warm clouds, where temperatures are above freezing, the collision coalescence process dominates. Larger cloud droplets fall faster than smaller ones, colliding and merging with them as they descend, growing in size until they are too heavy to remain suspended and fall as rain. In cold clouds, which are common in mid-latitudes and at higher altitudes, the Bergeron-Fine-Dyson process is at play. Here, supercooled water droplets, liquid water at temperatures below freezing, coexist with ice crystals. Ice crystals have a lower saturation vapor pressure than supercooled water, meaning they attract water vapor more readily. Water vapor evaporates from the supercooled droplets and deposits onto the ice crystals, causing the ice crystals to grow rapidly at the expense of the liquid droplets. These growing ice crystals then fall, either as snow or melting into rain if they pass through a warm layer of air. These precipitation events are integral parts of the Earth's complete water cycle, a continuous global process that endlessly circulates water between the oceans, atmosphere, and land. It begins with evaporation, where solar energy transforms liquid water into water vapor, rising into the atmosphere. This vapor then undergoes condensation, forming clouds. Precipitation follows, returning water to the Earth's surface as rain, snow, or other forms. Once on the surface, water may infiltrate the ground, flow as surface runoff into rivers and lakes, or be stored in glaciers and ice caps. Transpiration, the release of water vapor from plants, also contributes to atmospheric moisture. Ultimately, this water finds its way back to the oceans, completing the cycle, a constant vital exchange that sustains all life. The distribution and intensity of precipitation are influenced by a multitude of factors. Global air circulation patterns dictate broad zones of high and low rainfall. Topography plays a crucial role, with mountains forcing air to rise and cool, leading to increased precipitation on their windward sides and creating rain shadows on the leeward side. Proximity to large bodies of water provides a source of moisture, leading to higher precipitation along coastlines. Temperature also governs the form of precipitation and the capacity of the air to hold moisture. Furthermore, atmospheric stability and the presence of lifting mechanisms, such as frontal systems or convective heating, are essential for initiating the cloud formation and subsequent precipitation. The variability within the water cycle can lead to significant and often devastating weather phenomena, particularly drought and flood cycles. Droughts represent prolonged periods of unusually low precipitation, leading to water shortages, agricultural losses, and increased risk of wildfires. They can result from persistent high-pressure systems diverting storm tracks or long-term shifts in atmospheric circulation. Conversely, floods occur when excessive rainfall, rapid snowmelt, or storm surges overwhelm natural drainage systems, causing rivers to overflow and inundating land. These events are often linked to intense, slow-moving low-pressure systems or tropical cyclones. Both droughts and floods demonstrate the critical importance of a balanced water cycle and the profound impact that deviations from its norms can have on ecosystems and human societies, highlighting the fragility of our planet's hydrological equilibrium. The world's surface is not uniformly heated or moistened, leading to a mosaic of distinct climate zones, each characterized by its unique long-term weather patterns. These zones are broadly classified into categories like tropical, dry, temperate, continental, and polar, often further subdivided based on specific temperature and precipitation characteristics. Tropical climates found near the equator are consistently warm and often humid, supporting lush rainforests. Dry climates include deserts and steppes, marked by sparse rainfall. Temperate climates, in the mid-latitudes, experience distinct seasons with moderate temperatures and precipitation. Continental climates, far from oceanic influences, exhibit greater temperature extremes between summer and winter. Finally, polar climates at the highest latitudes are defined by persistent cold and ice. These classifications provide a framework for understanding the planet's diverse ecological systems and human adaptations. The most significant factor determining a region's climate and weather is its latitude, its distance from the equator. Near the equator, solar radiation is most direct and intense, leading to consistently warm temperatures and high evaporation rates, which in turn fuel frequent convection and abundant rainfall in the tropical zone. As latitude increases, the sun's rays strike the Earth at a more oblique angle, spreading the same amount of energy over a larger area and thus reducing its intensity. This decrease in solar energy leads to progressively cooler temperatures towards the poles, influencing everything from growing seasons to the prevalence of ice and snow, fundamentally shaping the types of ecosystems that can thrive. Seasonal weather patterns, the predictable shifts in temperature, precipitation, and daylight hours throughout the year, are primarily caused by the Earth's axial tilt of approximately 23.5 degrees relative to its orbital plane around the Sun. As the Earth revolves, different parts of the planet are tilted towards or away from the Sun, leading to variations in the directness of solar radiation. When a hemisphere is tilted towards the Sun, it experiences summer with longer days and more direct sunlight. When it's tilted away, it experiences winter with shorter days and less direct sunlight. This tilt, rather than the Earth's varying distance from the Sun, is the true orchestrator of our annual cycle of seasons, driving the predictable ebb and flow of weather across much of the globe. Within these broad climate zones, smaller localized variations known as microclimates can exist, creating unique weather conditions over very small areas. A microclimate might be found in a city, where buildings and paved surfaces absorb and radiate more heat, creating an urban heat island effect that makes the city warmer than surrounding rural areas. A forested valley might be cooler and more humid than an exposed hilltop just a short distance away. The orientation of a slope to the sun, the presence of a body of water, or even the density of vegetation can all contribute to distinct microclimates, demonstrating that weather is not just a global phenomenon, but also an incredibly localized experience, often differing significantly within a few hundred meters. Just as they influence global temperature, ocean currents exert a profound impact on regional climates. The warm Gulf Stream, originating in the tropics, carries heat northeastward across the Atlantic, making the climates of Western Europe significantly milder and wetter than other regions at similar latitudes. Without its warming influence, Cities like London and Paris would have climates more akin to Labrador or Siberia. Conversely, the cold California current flowing southward along the North American west coast contributes to the cool, foggy conditions prevalent in coastal California. These massive oceanic rivers act as thermal regulators, redistributing heat and moisture across the planet, creating stark climatic differences between coastal regions and altering the very character of the weather experienced in those areas. Modern meteorology has transformed weather forecasting from an art based on observation into a sophisticated science, leveraging an array of advanced tools and technologies. Satellites orbiting Earth continuously monitor cloud patterns, atmospheric temperatures, moisture content, and even wind speeds from space, providing a global perspective that is impossible from the ground. Radar systems, particularly Doppler radar, are instrumental in detecting precipitation, measuring its intensity, and tracking the movement of storms, even discerning wind shear within thunderstorms that can indicate tornado formation. These technologies provide the raw, real-time data that forms the backbone of contemporary weather prediction. Satellite and radar systems work in concert to provide a comprehensive view of the atmosphere. Geostationary satellites positioned high above the equator offer continuous views of an entire hemisphere, capturing the evolution of large-scale weather systems like hurricanes. Polar orbiting satellites provide higher-resolution images and data from colder regions, filling in details missed by their geostationary counterparts. Ground-based radar emits microwave pulses that bounce off precipitation particles, allowing meteorologists to visualize storms, estimate rainfall rates, and even infer wind velocities within severe weather, giving crucial lead time for warnings. This combined approach allows for both broad-scale monitoring and detailed local analysis, enhancing the accuracy and timeliness of forecasts. At the heart of modern weather forecasting lies computer modeling, a complex process known as numerical weather prediction. Supercomputers take the vast amounts of data collected from satellites, radar, weather balloons, and ground stations and input them into sophisticated mathematical models of the atmosphere. These models are based on the fundamental laws of physics and fluid dynamics, simulating how the atmosphere will evolve over time. By running these complex equations forward, meteorologists can generate forecasts for temperature, pressure, wind, and precipitation for various time horizons, from short-range hourly predictions to extended outlooks spanning several weeks, though accuracy generally diminishes with time. Despite the prowess of advanced technology, traditional weather prediction methods, honed over centuries of human observation, still hold a certain wisdom. Mariners and farmers, intimately connected to the elements, learn to interpret changes in wind direction, the appearance of specific cloud types, or the behavior of animals as harbingers of weather shifts. The old adage, "Red sky at night, sailors delight. Red sky in morning, sailors take warning," often has a scientific basis, related to dust and moisture levels in the atmosphere. While these methods lack the precision of modern tools, they offer a localized, immediate understanding of atmospheric nuances that can complement, though not replace, scientific forecasting. However, even with all these advancements, weather forecasting still has its inherent limitations and is not an exact science. The atmosphere is a chaotic system, meaning that tiny, unmeasurable variations in initial conditions can lead to vastly different outcomes over time, a concept famously known as the butterfly effect. The resolution of computer models, while continually improving, cannot capture every microscale atmospheric process. Therefore, forecasts always carry a degree of uncertainty, which increases with the forecast period. While short-range forecasts are remarkably accurate, predicting specific conditions weeks or months in advance remains a significant challenge, reminding us that the atmosphere, for all our tools, retains an element of unpredictability. Weather is not merely an abstract phenomenon. It intimately shapes the fabric of our daily lives, influencing everything from our mood to our economic stability. Our physical comfort and health are directly tied to atmospheric conditions. High temperatures and humidity can lead to heat stroke and dehydration, while extreme cold can cause hypothermia and frostbite. Air quality, heavily influenced by weather patterns that can trap pollutants or disperse them, impacts respiratory health. Even our psychological well-being is affected, with some individuals experiencing seasonal affective disorder during periods of reduced sunlight, demonstrating the profound connection between the atmosphere and the human condition. The agricultural sector, the very foundation of our food supply, is profoundly dependent on the whims of weather. Farmers rely on predictable patterns of rainfall and sunlight for successful crop growth. Droughts can devastate harvests, leading to food shortages and economic hardship, while excessive rain or hail can ruin crops just before harvest. Temperature extremes, both hot and cold, can stress livestock and damage delicate plants. The timing of frosts, the severity of growing seasons, and the prevalence of pests and diseases, all influenced by weather, dictate the productivity and profitability of farms, directly impacting the availability and cost of food for populations worldwide. Transportation and infrastructure, the arteries of modern society, are highly vulnerable to adverse weather. Heavy snowfall can shut down airports and roads, stranding travelers and disrupting supply chains. Dense fog can reduce visibility to dangerous levels, leading to accidents. High winds can make bridges impassable and severely impact air travel. Flooding can wash out roads, railways and bridges, isolating communities and causing immense repair costs. Even seemingly benign phenomena like ice accumulation can bring down power lines, highlighting how deeply interwoven weather is with the functioning and resilience of our built environment. Weather-related natural disasters represent some of the most destructive forces on Earth, demanding constant vigilance and preparation. Hurricanes and typhoons bring catastrophic winds, storm surges and torrential rain, causing widespread destruction and loss of life in coastal areas. Tornadoes, though localized, can flatten entire communities in minutes. Blizzards can paralyze vast regions, while prolonged droughts can lead to dust storms and exacerbate wildfires. Earthquakes and volcanic eruptions, while not weather phenomena themselves, can interact with weather to create additional hazards like ashfall. Effective early warning systems, robust infrastructure, and community preparedness are crucial for mitigating the devastating impact of these extreme events. Even something as personal as our sleep and overall well-being can be significantly impacted by weather, prompting us to adapt our routines for optimal comfort. High humidity and warm temperatures can make falling asleep difficult, as the body struggles to cool itself, leading to restless nights. Conversely, excessively dry air can irritate respiratory passages. Many find the gentle patter of rain or the distant rumble of thunder to be naturally soothing, aiding relaxation. Understanding these subtle influences allows us to make conscious choices, such as adjusting indoor temperatures, using humidifiers or dehumidifiers, or even choosing specific bedding to create an environment conducive to better sleep and overall health, demonstrating our continuous, often unconscious, adaptation to the ever-present forces of the atmosphere. The pervasive influence of weather extends far beyond the immediate physical sensations, subtly shaping our cultural expressions, architectural designs, and even our economic landscapes. Consider, for instance, the profound impact of monsoon seasons in South Asia, where the rhythmic arrival of rains dictates agricultural cycles, inspires religious festivals, and even influences fashion and cuisine. The entire social fabric of these regions is interwoven with the expectation and celebration of the monsoon, a period of vital renewal that replenishes water sources and sustains livelihoods. Without these seasonal rains, life as it is known would simply cease to exist, illustrating a fundamental dependency that has been etched into generations of human experience. Conversely, the harsh realities of prolonged droughts in arid regions have compelled communities to develop innovative water conservation techniques, from ancient underground aqueducts, known as qanats, to modern desalination plants. These ingenious adaptations are not merely technological fixes. They represent a deep understanding of environmental limitations and a collective commitment to survival in the face of scarcity. The architecture in these areas often features thick walls and small windows to keep interiors cool, reflecting centuries of accumulated wisdom about climate control. Our homes, in effect, become extensions of our atmospheric adaptation, designed to buffer us from the extremes of heat or cold. The very concept of migration, both historical and contemporary, is often inextricably linked to weather patterns and climate shifts. Ancient civilizations followed seasonal animal migrations, which themselves were driven by weather-dependent food sources. More recently, climate change has emerged as a significant driver of human displacement, with communities forced to abandon ancestral lands due to rising sea levels, desertification, or increasingly frequent and intense storms. These migrations are not just statistics. They represent immense human stories of resilience, loss, and the desperate search for habitable environments. The human spirit, in its perpetual quest for security and sustenance, is constantly negotiating with, and often reshaping, the natural world in response to atmospheric pressures. Even our daily routines and psychological states are deeply intertwined with the prevailing weather. The phenomenon of seasonal affective disorder, or SAD, is a testament to the profound influence of light and temperature on human mood and well-being. The long, dark days of winter in higher latitudes can trigger feelings of lethargy and sadness in susceptible individuals, highlighting the biological imperative for adequate sunlight exposure. Conversely, a bright sunny day can elevate spirits and encourage outdoor activity, fostering a sense of vitality and connection with the natural world. This bidirectional relationship means that just as weather affects us, our collective human activities, particularly industrialization and consumption, are now undeniably altering global weather patterns, leading to a complex feedback loop that demands our urgent attention. The intricate dance between human society and atmospheric phenomena is perhaps nowhere more evident than in the realm of agriculture. For millennia, human survival has hinged on our ability to cultivate crops, a process utterly dependent on favorable weather conditions. The advent of farming itself was a monumental leap in human history, allowing for settled communities and the development of complex societies, but it also tethered our fate to the whims of rain, sun, and temperature. A single season of drought or excessive rainfall could spell famine and societal collapse, a stark reminder of our enduring vulnerability. Today, while technology offers some buffer against immediate weather shocks, the fundamental dependency remains. Modern agriculture employs sophisticated weather forecasting models to optimize planting and harvesting schedules, to predict disease outbreaks linked to humidity, and to anticipate the need for irrigation. Precision agriculture, utilizing satellite imagery and localized weather data, tailors interventions to specific microclimates within a single field, maximizing yields and minimizing waste. Yet, despite these advancements, large-scale droughts, floods, and unseasonal frosts continue to inflict billions of dollars in losses annually and threaten global food security. The very foundation of our sustenance is built upon a delicate atmospheric balance, a balance that is increasingly being disturbed by human actions. Consider the historical impact of phenomena like El Niño, a naturally occurring climate pattern that originates in the Pacific Ocean but has far-reaching effects on global weather. Its warm phase, characterized by warmer-than-average sea surface temperatures, can trigger droughts in some regions and heavy rainfall in others, disrupting agricultural cycles across continents. The Peruvian anchovy fishery, a cornerstone of its economy, is particularly vulnerable, as El Niño conditions push nutrient-rich cold waters deeper, scattering the anchovy populations. The global commodity markets react to these shifts, with prices of staple crops fluctuating based on anticipated yields in affected regions. This interconnectedness demonstrates how a single atmospheric oscillation can send ripple effects through economies and food systems worldwide, emphasizing the need for robust international cooperation in monitoring and responding to these large-scale phenomena. Beyond agriculture, our infrastructure is a testament to our ongoing negotiation with weather. Every bridge, road, and building is designed with specific climatic considerations in mind. In regions prone to heavy snowfall, roofs are steeply pitched to prevent accumulation and collapse. In earthquake-prone areas, structures are engineered to withstand ground motion, often exacerbated by rain-saturated soil. Coastal communities build seawalls and elevate homes to protect against storm surges and rising sea levels, a direct response to the increasing intensity of hurricanes and typhoons. The materials chosen for construction, from heat-absorbing dark asphalt in cold climates to reflective light-colored roofs in hot ones, are all deliberate choices shaped by the prevailing weather. The sheer scale of investment in weather-resistant infrastructure underscores our collective vulnerability and our continuous effort to create safe and resilient living environments. However, as climate change accelerates, the goalposts are shifting. Infrastructure designed for historical weather patterns may prove inadequate for the more extreme and unpredictable conditions of the future. Roads buckle under unprecedented heat waves, drainage systems are overwhelmed by torrential downpours, and power grids fail when confronted with superstorms. This necessitates a proactive approach to urban planning and engineering, integrating climate resilience into every design and development decision, recognizing that our built environment must adapt as rapidly as the climate itself is changing. The cultural narratives and artistic expressions of various societies are also deeply imbued with weather symbolism. In many cultures, rain is a symbol of fertility and renewal, celebrated in songs, dances, and rituals. The sun often represents life, warmth, and divine power. Storms, while destructive, can also be seen as cleansing forces or as manifestations of powerful deities. These symbolic interpretations are not arbitrary. They emerge from generations of direct experience with the weather, shaping our collective consciousness and providing a framework for understanding our place in the natural world. From ancient myths describing sky gods and weather spirits, to contemporary novels and films that use weather as a powerful narrative device, the atmosphere permeates our storytelling. A foggy landscape can evoke mystery, a raging storm can symbolize inner turmoil, and a clear sunny day can represent hope and new beginnings. These artistic representations serve not only as reflections of our relationship with weather, but also as a means of processing and communicating our experiences, anxieties, and aspirations related to the environment. They remind us that weather is not just a scientific phenomenon, it is a deeply human experience, intrinsically linked to our emotions, our history, and our very identity. Even the seemingly mundane aspects of daily life, like leisure activities and fashion, are dictated by the weather. A sudden downpour can cancel outdoor plans, shifting our focus to indoor entertainment. The choice of clothing, from heavy winter coats to light summer dresses, is a direct response to temperature and precipitation. Entire industries, such as tourism and outdoor recreation, are heavily weather-dependent. Ski resorts thrive on abundant snowfall, while beach destinations rely on sunny skies. Unpredictable weather patterns can lead to significant economic losses for these sectors, highlighting the pervasive financial implications of atmospheric variability. The commercial world, too, is a mirror reflecting atmospheric influences. Retailers adjust their inventory based on seasonal weather forecasts, stocking warmer clothes in anticipation of a cold front or more air conditioners during a predicted heat wave. Energy companies meticulously track temperature predictions to manage demand for heating and cooling, ensuring stable power grids. The insurance industry, perhaps more than any other, is directly exposed to the financial risks associated with extreme weather events, constantly adjusting premiums and policies in response to escalating climate-related damages. This intricate web of economic activity, from the smallest local business to multinational corporations, is constantly calibrating its operations in response to the dynamic and often unpredictable forces of the atmosphere. The very air we breathe, an invisible but vital component of weather, directly impacts our health. Air quality, determined by the concentration of pollutants, is heavily influenced by meteorological conditions. Stagnant air masses under high-pressure systems can trap pollutants close to the ground, leading to smog and exacerbating respiratory illnesses. Wind dispersion, on the other hand, can help clear the air. Temperature inversions, where a layer of warm air sits above cooler air, act like a lid, preventing pollutants from rising and dispersing, leading to dangerous air quality episodes. Understanding these atmospheric dynamics is critical for public health initiatives, allowing for timely warnings and interventions to protect vulnerable populations. The increasing frequency and intensity of heat waves, a direct consequence of global warming, pose severe health risks, particularly for the elderly, young children, and those with pre-existing medical conditions. Heat stroke, dehydration, and cardiovascular strain become more prevalent, placing immense pressure on healthcare systems. Conversely, prolonged exposure to extreme cold can lead to hypothermia and frostbite. These health impacts are not uniformly distributed. Socioeconomic factors often amplify vulnerability, with marginalized communities disproportionately affected due to inadequate housing, limited access to cooling or heating, and lack of healthcare. This highlights the social justice dimension of climate change, where weather impacts are not merely environmental but deeply intertwined with issues of equity and access. Even the spread of infectious diseases can be linked to weather patterns. Mosquito-borne illnesses like malaria and dengue fever are highly sensitive to temperature and rainfall, as these factors influence mosquito breeding rates and viral replication within the insect. Warmer temperatures can expand the geographical range of these vectors, bringing diseases to previously unaffected areas. Droughts can force populations to rely on contaminated water sources, increasing the risk of waterborne diseases. The study of how climate influences disease ecology, known as medical geography, is becoming increasingly vital in a world grappling with a changing climate and emerging infectious threats. This connection underscores the complex and often indirect ways in which atmospheric phenomena shape human well-being and survival. The ocean, an immense reservoir of heat and moisture, acts as a global weather engine, influencing climate patterns across the planet. Ocean currents, driven by temperature and salinity differences, transport heat from the equator towards the poles, moderating temperatures in coastal regions. The Gulf Stream, for instance, is responsible for the relatively mild climate of Western Europe, despite its high latitude. Changes in these currents, potentially driven by melting glaciers and altered freshwater inputs, could have profound impacts on regional climates, leading to colder winters or warmer summers in areas accustomed to specific conditions. The interaction between the ocean and atmosphere is a continuous exchange of energy and matter. Evaporation from the ocean surface provides the moisture for rainfall, while ocean temperatures influence the formation and intensity of tropical cyclones. The ocean also acts as a massive carbon sink, absorbing a significant portion of anthropogenic carbon dioxide emissions, thereby mitigating some of the effects of global warming. However, this absorption comes at a cost, leading to ocean acidification, which threatens marine ecosystems and the livelihoods that depend on them. Understanding this intricate ocean-atmosphere coupling is paramount to accurately predict future weather and climate trends, and to devise effective strategies for climate change mitigation and adaptation. The very composition of our atmosphere, a delicate balance of gases, is fundamental to life on Earth and the weather systems that sustain it. Nitrogen and oxygen, making up the vast majority, are relatively stable. However, trace gases like water vapor, carbon dioxide, methane, and nitrous oxide, known as greenhouse gases, play a disproportionately significant role in regulating Earth's temperature. These gases trap outgoing long-wave radiation, preventing it from escaping into space and thus warming the planet. Without the natural greenhouse effect, Earth would be a frozen, uninhabitable world. The problem arises when human activities, primarily the burning of fossil fuels, deforestation, and industrial processes, significantly increase the concentration of these greenhouse gases beyond natural levels. This anthropogenic enhancement of the greenhouse effect leads to global warming, which in turn alters weather patterns. More energy is trapped in the climate system, leading to more intense heat waves, more extreme rainfall events, and changes in atmospheric circulation that can influence everything from hurricane tracks to drought frequency. The scientific consensus on this issue is overwhelming, underscoring the urgent need for a global transition to sustainable energy sources and land use practices to preserve the delicate atmospheric balance that supports all life. The science of meteorology, the study of weather, has evolved dramatically over centuries, transforming from anecdotal observations to highly sophisticated predictive models. Early civilizations relied on empirical observations of cloud formations, wind directions, and animal behavior to forecast local weather. The invention of instruments like the barometer, thermometer, and anemometer in the 17th and 18th centuries provided quantitative measurements, laying the groundwork for a more scientific approach. The development of telegraphy in the 19th century allowed for the rapid collection and dissemination of weather data across wider areas, leading to the first weather maps and regional forecasts. The 20th century witnessed an explosion of technological advancements that revolutionized meteorology. The advent of radiosondes, weather balloons equipped with instruments, provided vertical profiles of the atmosphere. Radar technology allowed for the detection of precipitation and storm structures. Satellite imagery, starting in the 1960s, offered a global perspective of weather systems, tracking hurricanes and monitoring large-scale atmospheric phenomena. Today, supercomputers crunch vast datasets from thousands of sensors, satellites, and radar stations, running complex atmospheric models to produce increasingly accurate forecasts, from short-range predictions to long-term climate projections. This continuous pursuit of understanding and prediction is a testament to our enduring fascination with and dependence on the weather. However, despite these remarkable advancements, weather forecasting remains an inherently challenging endeavor due to the chaotic nature of the atmosphere. The butterfly effect, a concept from chaos theory, illustrates how a tiny perturbation in one part of the system can have widespread and unpredictable consequences elsewhere. While deterministic chaos means that perfect, infinitely long-range forecasts are impossible, the increasing understanding of atmospheric physics and the availability of more powerful computational resources continue to push the boundaries of predictability. Ensemble forecasting, which runs multiple model simulations with slightly varied initial conditions, provides a range of possible outcomes and probabilistic forecasts, giving forecasters a better sense of uncertainty and confidence levels. This blend of scientific rigor and probabilistic reasoning is essential for navigating the inherent complexities of atmospheric dynamics and providing actionable information for decision-making across various sectors. The very concept of climate differs fundamentally from weather. While weather describes the atmospheric conditions at a specific place and time, climate refers to the long-term average of weather patterns in a region, typically over a period of 30 years or more. Climate defines the expected range of temperatures, precipitation, and other atmospheric variables that characterize a particular geographical area. It is the backdrop against which daily weather events unfold. For example, a single cold snap in Florida is a weather event, but the overall pattern of warm, humid conditions throughout the year defines its tropical climate. Understanding this distinction is crucial when discussing climate change. A single unusually hot summer or a particularly harsh winter does not in itself prove or disprove climate change. Instead, climate change refers to a significant and lasting shift in these long-term average weather patterns. This shift is evidenced by rising global average temperatures, changes in precipitation regimes, more frequent and intense extreme weather events, and melting glaciers and ice sheets. The observed trends over decades and centuries, not isolated events, provide the compelling evidence for a changing climate, driven primarily by human activities that alter the Earth's energy balance. The study of paleoclimatology, the examination of past climates, provides invaluable context for understanding current climate change. Scientists use various proxy data sources, such as ice cores, tree rings, sediment layers, and coral reefs to reconstruct past temperatures, atmospheric composition, and precipitation patterns stretching back hundreds of thousands, even millions of years. Ice cores, for instance, trap ancient air bubbles, allowing scientists to directly measure past atmospheric concentrations of greenhouse gases, revealing a strong correlation between these gases and global temperatures throughout Earth's history. These paleoclimate records demonstrate that Earth's climate has naturally varied over geological timescales, with periods of warmth and glaciation. However, the current rate and magnitude of warming, particularly over the last century, are unprecedented in the paleoclimate record. The speed at which greenhouse gas concentrations are increasing due to human emissions far exceeds any natural fluctuations observed in the past. This historical perspective underscores the exceptional nature of the current climate crisis and provides compelling evidence that the changes we are witnessing today are not simply part of a natural cycle, but are driven by anthropogenic forcings, fundamentally altering the planet's atmospheric systems. The societal implications of a changing climate are vast and interconnected, touching upon almost every aspect of human life. Food security is threatened by altered growing seasons, increased pest outbreaks, and more frequent droughts and floods. Water resources are under pressure from changes in precipitation patterns and glacier melt, leading to potential conflicts over scarce supplies. Coastal communities face the existential threat of rising sea levels and more powerful storm surges, necessitating costly adaptation measures or even relocation. Vector-borne diseases are expanding their range, posing new public health challenges. Economically, the costs associated with climate change are staggering, encompassing everything from disaster relief and infrastructure repair to lost productivity and ecosystem services. Vulnerable populations and developing nations, often least responsible for historical emissions, are disproportionately impacted, exacerbating existing inequalities and potentially leading to mass migrations and social unrest. The stability of geopolitical relations can be strained as nations compete for diminishing resources or grapple with climate-induced humanitarian crises. Addressing climate change is therefore not just an environmental imperative, but a profound challenge to global stability, human well-being, and social justice, requiring unprecedented levels of international cooperation and transformative societal change. The transition to a low-carbon economy represents one of the most significant challenges and opportunities of our time. It involves a fundamental shift away from fossil fuels towards renewable energy sources like solar, wind, hydropower, and geothermal. This transition requires massive investments in new technologies, infrastructure, and energy storage solutions. It also necessitates significant policy changes, including carbon pricing, regulations on emissions, and incentives for sustainable practices across all sectors, from transportation to manufacturing. Beyond energy, sustainable land use practices, such as reforestation and improved agricultural methods that sequester carbon, play a crucial role. Enhancing energy efficiency in homes, buildings, and industries can drastically reduce demand. Developing and deploying carbon capture technologies, though still in their nascent stages, may also contribute to mitigating emissions from hard-to-abate sectors. This transformation is not merely technological. It requires a paradigm shift in our relationship with energy, consumption, and the natural world, recognizing that our economic prosperity and long-term survival are inextricably linked to the health of our planet's atmospheric systems. Individual actions, though seemingly small, collectively contribute to both the problem and the solution. Making conscious choices about energy consumption, transportation, diet, and waste generation can reduce one's carbon footprint. Supporting businesses and policies that prioritize sustainability sends a clear signal to decision-makers. Engaging in advocacy, educating others, and participating in civil discourse around climate change are vital for fostering the collective will necessary for large-scale systemic change. However, it is crucial to recognize that individual efforts alone are insufficient to address a challenge of this magnitude. Systemic change, driven by government policies, corporate responsibility, and international agreements, is paramount. Individuals can act as catalysts for this change, demonstrating demand for sustainable products and services, holding leaders accountable, and pushing for ambitious climate action at all levels of governance. The interconnectedness of our global society means that actions taken in one part of the world can have ripple effects everywhere, highlighting the shared responsibility we all bear in shaping the future of our planet's weather and climate. The concept of geoengineering represents a controversial but increasingly discussed set of large-scale technological interventions designed to deliberately manipulate Earth's climate system to counteract global warming. These approaches generally fall into two main categories: carbon dioxide removal, CDR, and solar radiation management, SRM. CDR technologies aim to remove carbon dioxide directly from the atmosphere, effectively reversing some of the emissions that have already occurred. Examples include afforestation and reforestation, bioenergy with carbon capture and storage (BECS), and direct air capture (DACA) technologies. SRM techniques, on the other hand, aim to reflect a small percentage of incoming sunlight back into space, thereby cooling the planet. Proposed methods include stratospheric aerosol injection, which involves injecting reflective particles into the upper atmosphere, and marine cloud brightening, which seeks to increase the reflectivity of low-lying clouds. While geoengineering offers the potential to rapidly reduce global temperatures, it also carries significant risks and uncertainties, including potential unintended side effects on regional weather patterns, ecosystems, and geopolitical stability. The ethical implications, governance challenges, and the potential for moral hazard, where the prospect of geoengineering might reduce the urgency of emissions reductions, are profound subjects of ongoing debate and research. Ultimately, our relationship with weather is a fundamental aspect of the human experience, a constant negotiation with the natural forces that shape our lives. From the earliest hominids seeking shelter from storms, to modern societies grappling with the complexities of climate change, the atmosphere has always been a defining element of our existence. It influences our survival, our culture, our economies, and our very well-being. The challenge before us now is to transition from a passive adaptation to weather's whims to an active, responsible stewardship of the atmospheric systems that sustain us, ensuring a stable and habitable planet for generations to come. This requires not only scientific understanding and technological innovation, but also a profound shift in human values, recognizing our interconnectedness with the natural world and our shared responsibility for its future. The weather, in all its intricate glory and formidable power, serves as a constant reminder of this profound and enduring bond-onship with weather is a fundamental aspect of the human experience, a constant negotiation with the natural forces that shape our lives. From the earliest hominids seeking shelter from storms, to modern societies grappling with the complexities of climate change, the atmosphere has always been a defining element of our existence. It influences our survival, our culture, our economies, and our very well-being. The challenge before us now is to transition from a passive adaptation to weather's whims to an active, responsible stewardship of the atmospheric systems that sustain us, ensuring a stable and habitable planet for generations to come. This requires not only scientific understanding and technological innovation, but also a profound shift in human values, recognizing our interconnectedness with the natural world and our shared responsibility for its future. The weather, in all its intricate glory and formidable power, serves as a constant reminder of this profound and enduring bond. The Earth's atmosphere functions as a vast, intricate heat engine, perpetually working to redistribute solar energy across the planet's surface. This engine is powered by the sun, which delivers a staggering amount of radiation, primarily in the form of visible light to our world. However, this energy isn't distributed evenly. The equatorial regions receive a more direct and concentrated dose of sunlight throughout the year, leading to warmer temperatures, while the poles experience more oblique angles of incidence and longer periods of darkness, resulting in significantly colder conditions. This fundamental imbalance in solar heating is the primary driver of all weather phenomena, setting in motion a complex series of atmospheric and oceanic circulations that seek to equalize these temperature differences. Without this constant effort to balance the energy budget, the equator would become unbearably hot, and the poles would plunge into an even more frigid existence, rendering much of the planet uninhabitable. The journey of solar radiation begins high above the Earth, where it travels through the vacuum of space before encountering our atmosphere. A portion of this incoming solar radiation, known as insolation, is immediately reflected back into space by clouds, ice, snow, and even the bright surfaces of deserts. This reflectivity is quantified by a measure called albedo, with fresh snow having a very high albedo and dark ocean waters a very low one. The remaining solar energy penetrates the atmosphere, where some of it is absorbed by atmospheric gases like ozone, which brilliantly shields us from harmful ultraviolet radiation, and water vapor, which plays a crucial role in the greenhouse effect. The majority of the insolation, however, reaches the Earth's surface, where it is absorbed by land and oceans, causing them to warm. This absorption is not uniform. Darker surfaces absorb more heat, while lighter surfaces reflect more. Once the Earth's surface absorbs solar energy, it does not simply store it indefinitely. Instead, it re-emits this energy back into the atmosphere, but at a longer wavelength, primarily in the form of infrared radiation, which we perceive as heat. This re-emission is a critical step in the energy balance. Certain atmospheric gases, notably water vapor, carbon dioxide, methane and nitrous oxide, possess a unique property. They are largely transparent to incoming shortwave solar radiation, but are highly effective at absorbing outgoing long-wave infrared radiation. This phenomenon is known as the greenhouse effect, and it is absolutely essential for life on Earth. Without these naturally occurring greenhouse gases, our planet's average temperature would plummet to a frigid -18 degrees Celsius, making it a frozen wasteland incapable of supporting the vast biodiversity we see today. The greenhouse effect acts like a blanket, trapping some of the re-emitted heat and warming the lower atmosphere. However, the delicate balance of the natural greenhouse effect is currently being disrupted by human activities, primarily the burning of fossil fuels, deforestation, and industrial processes. These activities release additional greenhouse gases into the atmosphere, intensifying the natural warming and leading to a phenomenon known as anthropogenic climate change. This enhanced greenhouse effect is causing the Earth's average temperature to rise, leading to a cascade of observable impacts, including rising sea levels, more frequent and intense heat waves, altered precipitation patterns, and an increase in extreme weather events. Understanding the intricate dance between incoming solar radiation, atmospheric absorption and reflection, and the re-emission of infrared radiation is paramount to comprehending not only the fundamental workings of our weather, but also the profound implications of our impact on the planet's climate system. The differential heating of the Earth's surface creates temperature gradients, and these gradients are the fundamental drivers of atmospheric circulation. Warm air, being less dense, tends to rise, while cooler, denser air sinks. This simple principle of convection is the bedrock of many weather phenomena. At the equator, the intense solar radiation heats the surface and the air above it, causing it to expand and ascend. As this warm, moist air rises, it cools, and the water vapor within it condenses, forming towering cumulonimbus clouds and producing abundant rainfall. This upward movement of air creates a zone of low pressure at the surface, known as the Intertropical Convergence Zone, or ITCZ, a band of persistent thunderstorms and heavy precipitation that girdles the globe near the equator. As this equatorial air ascends, it eventually reaches the tropopause, the boundary between the troposphere and the stratosphere, where it can no longer rise. It then begins to spread out poleward, flowing horizontally in the upper atmosphere. As it moves away from the equator, it gradually cools and dries. Around 30 degrees latitude in both the northern and southern hemispheres, this cooler, denser air begins to sink back towards the surface. This descending air creates zones of high pressure, characterized by clear skies, dry conditions, and often warm temperatures. These subtropical high-pressure belts are where many of the world's major deserts are located, such as the Sahara in Africa and the Atacama in South America, a direct consequence of the dry, sinking air. Upon reaching the surface, this subsiding air then flows back towards the equator, completing a vast circulation loop known as the Hadley cell. These surface winds, deflected by the Coriolis effect, are known as the trade winds, historically crucial for sailing vessels traversing the oceans. The Coriolis effect, a consequence of the Earth's rotation, deflects moving objects including air and ocean currents to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is not a force in itself, but rather an apparent force arising from observations made from a rotating frame of reference. It plays a pivotal role in shaping the direction of global wind patterns and ocean currents, influencing everything from the path of hurricanes to the distribution of marine life. Beyond the Hadley cells, two other major atmospheric circulation cells exist, the ferrule cell and the polar cell. The ferrule cell, located between approximately 30 and 60 degrees latitude, is a more complex and less direct circulation. It is largely driven by the interaction between the Hadley cell and the polar cell, acting as a kind of atmospheric gear in the middle latitudes. In this cell, surface winds, again influenced by the Coriolis effect, flow poleward and eastward, forming the prevailing westerlies which are responsible for much of the weather patterns experienced in temperate regions. These westerlies are often associated with the movement of frontal systems and mid-latitude cyclones, bringing variable weather conditions. The polar cell, situated beyond 60 degrees latitude, is characterized by cold, dense air sinking at the poles, creating high-pressure zones. This cold air then flows equatorward along the surface, forming the polar easterlies. As this cold air moves towards lower latitudes, it eventually encounters the warmer air flowing poleward from the ferrule cell. The meeting point of these two air masses, characterized by a steep temperature gradient, forms the polar front, a dynamic and often turbulent boundary where much of the stormy weather in the high latitudes originates. This intricate system of three circulation cells in each hemisphere, driven by differential heating and modulated by the Earth's rotation, is a simplified yet powerful model for understanding the large-scale patterns of atmospheric movement. and their profound influence on global climate and regional weather. The oceans also play an indispensable role in the global heat engine, acting as a massive heat reservoir and conveyor belt. Water has a much higher specific heat capacity than land, meaning it can absorb and store a tremendous amount of heat energy without experiencing significant temperature changes. This property makes the oceans crucial in moderating global temperatures. They absorb vast quantities of solar radiation, particularly in tropical regions, and then slowly release this heat back into the atmosphere over extended periods, influencing coastal climates and global weather patterns. The sheer volume of the oceans means that they can store an immense amount of energy, buffering the planet against more extreme temperature swings. Ocean currents, both at the surface and in the deep, are another vital component of this heat distribution system. Surface currents are primarily driven by prevailing winds, which drag the uppermost layers of the ocean along with them. The Coriolis effect once again deflects these currents, creating large circulating gyres in each ocean basin. A prime example is the Gulf Stream in the North Atlantic, a powerful warm ocean current that originates in the Gulf of Mexico and flows northeastward along the eastern coast of North America before crossing the Atlantic towards Europe. This current transports an enormous amount of heat, significantly moderating the climate of Western Europe, making it much warmer than other regions at similar latitudes. Without the Gulf Stream, cities like London and Paris would experience much harsher, colder winters, resembling those of Labrador or Siberia. Below the surface, a slower, more deliberate circulation system operates, driven by differences in water density. This is the thermohaline circulation, often referred to as the global conveyor belt. It is a vast, interconnected system of ocean currents that moves water throughout all the world's oceans, affecting global climate over timescales of decades to centuries. Thermohaline circulation is initiated in polar regions where cold, salty water, made denser by the formation of sea ice which leaves salt behind, sinks to the ocean floor. This deep, cold water then flows slowly across the ocean basins, eventually resurfacing in other parts of the world through a process called upwelling, bringing nutrient-rich waters to the surface and supporting vibrant marine ecosystems. This deep ocean circulation plays a critical role in sequestering carbon dioxide from the atmosphere and distributing heat throughout the planet's deep oceans, further regulating global temperatures. The interaction between the atmosphere and the oceans is a continuous, dynamic feedback loop. Atmospheric processes influence ocean currents and temperatures, and in turn, ocean conditions profoundly affect the atmosphere. For instance, warmer ocean waters can lead to increased evaporation, supplying more moisture to the atmosphere, which can fuel more intense rainfall and tropical cyclones. Conversely, strong winds can stir up ocean waters, bringing cooler water to the surface and influencing localized atmospheric temperatures. El Niño and La Niña events, which are periodic fluctuations in sea surface temperatures in the equatorial Pacific Ocean, are prime examples of this powerful ocean-atmosphere coupling. These phenomena have far-reaching impacts on weather patterns across the globe, influencing rainfall, temperatures, and the frequency of extreme weather events in distant regions. The global heat engine, therefore, is not a collection of isolated components, but a highly interconnected and interdependent system. The sun's energy drives the initial differential heating, which in turn sets the atmosphere and oceans in motion. These atmospheric and oceanic circulations then work in concert to redistribute heat and moisture, creating the diverse array of climates and weather patterns we observe across the planet. Understanding this intricate interplay of forces and processes is fundamental to predicting weather, comprehending climate change, and ultimately to ensuring the sustainable management of our planetary resources. The sheer scale and complexity of this global engine are a testament to the dynamic and self-regulating nature of Earth's systems, a constant reminder of the profound interconnectedness of all natural phenomena. Every gust of wind, every drop of rain, and every ray of sunshine is a manifestation of this grand planetary effort to maintain an energy balance, a delicate equilibrium that sustains life in all its myriad forms. But a highly interconnected and interdependent system. The sun's energy drives the initial differential heating, which in turn sets the atmosphere and oceans in motion. These atmospheric and oceanic circulations then work in concert to redistribute heat and moisture, creating the diverse array of climates and weather patterns we observe across the planet. Understanding this intricate interplay of forces and processes is fundamental to predicting weather, comprehending climate change, and ultimately to ensuring the sustainable management of our planetary resources. The sheer scale and complexity of this global engine are a testament to the dynamic and self-regulating nature of Earth's systems, a constant reminder of the profound interconnectedness of all natural phenomena. Every gust of wind, every drop of rain, and every ray of sunshine is a manifestation of this grand planetary effort to maintain an energy balance, a delicate equilibrium that sustains life in all its myriad forms. This intricate dance begins with the sun, a fiery furnace billions of miles away, yet its impact on our planet is undeniably intimate and profound. The sun's radiation, primarily in the form of visible light and ultraviolet rays, penetrates Earth's atmosphere, but not uniformly. The angle at which these rays strike the planet's surface is a critical factor in determining how much energy is absorbed. Near the equator, sunlight hits Earth almost perpendicularly, concentrating its energy over a smaller area and leading to warmer temperatures. As we move towards the poles, the same amount of solar radiation is spread over a much larger surface area due to the curvature of the Earth, resulting in less intense heating and consequently colder conditions. This fundamental disparity in solar insolation creates a vast temperature gradient from the equator to the poles, a primary driver of atmospheric and oceanic circulation. However, the atmosphere is not a passive recipient of solar energy. Gases like water vapor, carbon dioxide, methane, and nitrous oxide, collectively known as greenhouse gases, play a crucial role in trapping some of the outgoing infrared radiation emitted by Earth's surface. Without this natural greenhouse effect, our planet would be a frozen, lifeless wasteland, with an average temperature far below freezing. Yet an excessive concentration of these gases, largely due to human activities, leads to an enhanced greenhouse effect, causing global warming and disrupting the delicate energy balance. The atmosphere also acts as a filter, absorbing harmful ultraviolet radiation through the ozone layer, protecting life on the surface from its damaging effects. Clouds, composed of countless tiny water droplets or ice crystals, further modulate the amount of solar radiation reaching the surface. They reflect a significant portion of incoming sunlight back into space, contributing to a cooling effect, but they also trap outgoing infrared radiation, leading to a warming effect, especially at night. The net effect of clouds on Earth's energy budget is a complex area of ongoing research, highlighting the multifaceted nature of atmospheric processes. Once solar energy is absorbed by the Earth's surface, it is then re-radiated as infrared radiation, warming the lower atmosphere. This heated air becomes less dense and begins to rise, a process known as convection. Conversely, cooler, denser air sinks. This constant vertical movement of air creates convection currents, which are fundamental to weather patterns. At the equator, intense solar heating causes large masses of air to ascend, forming a low-pressure zone. As this warm, moist air rises, it cools and condenses, leading to the formation of towering cumulonimbus clouds and frequent heavy rainfall, characteristic of tropical regions. This rising air then flows poleward in the upper atmosphere, gradually cooling and becoming denser. Around 30 degrees latitude, this cooler, drier air descends, creating high-pressure zones. These descending air masses suppress cloud formation and precipitation, leading to the formation of the world's major deserts, such as the Sahara and the Arabian Desert. This large-scale circulation pattern, known as the Hadley cell, is one of the foundational elements of global atmospheric circulation. Beyond the Hadley cells, two other major circulation patterns complete the picture: the Ferrel cell and the polar cell. The Ferrel cell, situated in the mid-latitudes between 30 and 60 degrees, is a more complex and less direct circulation. It's often described as a reversal of the Hadley cell, driven indirectly by the interaction between the Hadley and polar cells. Warm air from the subtropics meets cold air from the polar regions in this zone, leading to significant weather variability and the formation of frontal systems. The polar cell, extending from 60 degrees latitude to the poles, is characterized by cold, dense air sinking at the poles, flowing equatorward along the surface, and rising at around 60 degrees latitude. This rising air then returns poleward in the upper atmosphere. These three cells, working in concert, are responsible for the broad distribution of temperature and precipitation across the globe, defining Earth's major climate zones. However, the Earth's rotation introduces another layer of complexity to these atmospheric movements. The Coriolis effect, an apparent force resulting from the planet's rotation, deflects moving objects including air and ocean currents to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is crucial in shaping the direction of winds and ocean currents. Instead of flowing directly from high to low pressure, winds are deflected, giving rise to the prevailing wind patterns we observe. For instance, in the northern hemisphere, the Coriolis effect deflects the poleward moving air in the upper part of the Hadley cell to the east, creating the westerly jet streams. Similarly, the equatorward moving air near the surface in the Hadley cell is deflected to the west, forming the trade winds which were historically vital for sailing ships. The Coriolis effect also plays a critical role in the formation and rotation of large-scale weather systems like cyclones and anticyclones. dictating their characteristic spiral patterns. The oceans, with their immense heat capacity, act as a massive heat reservoir and play an equally crucial role in the global energy balance. Ocean currents, both surface and deep ocean, are driven by a combination of prevailing winds, differences in water density due to temperature and salinity variations, and the Coriolis effect. The Gulf Stream, a powerful warm ocean current originating in the Gulf of Mexico, transports vast amounts of heat northward along the eastern coast of North America and across the Atlantic to Europe. This significantly moderates the climate of Western Europe, making it much milder than other regions at similar latitudes. Conversely, cold ocean currents like the California Current bring cooler temperatures to coastal regions. The deep ocean circulation, often referred to as the thermo-haline circulation because it's driven by differences in temperature, thermo, and salinity, haline, is a slow but monumental conveyor belt that transports water and heat around the entire globe. This global ocean conveyor belt can take centuries to complete a full cycle, playing a vital role in regulating Earth's climate on longer timescales. The interaction between the atmosphere and the oceans is a continuous and dynamic exchange of energy, moisture, and gases. Evaporation from the ocean surface transfers vast quantities of water vapor into the atmosphere, fueling cloud formation and precipitation. Conversely, precipitation over the oceans influences salinity levels, impacting ocean currents. The ocean also absorbs a significant portion of anthropogenic carbon dioxide from the atmosphere, acting as a crucial carbon sink, though this absorption also leads to ocean acidification, with detrimental effects on marine ecosystems. These interconnected systems are constantly influencing each other, creating a complex feedback loop where changes in one component can ripple through the entire system, leading to both localized weather events and global climate shifts. Consider the intricate dance of a thunderstorm. It begins with intense solar heating of the ground, warming the air above it. This warm, moist air, being less dense, rises rapidly. As it ascends, it cools, and the water vapor within it condenses, forming cumulus clouds. If the upward motion is strong and continuous, these cumulus clouds can grow vertically into towering cumulonimbus clouds, often reaching the tropopause, the boundary between the troposphere and the stratosphere. Within these immense clouds, strong updrafts and downdrafts develop, creating turbulent conditions. Ice crystals and water droplets collide, generating electrical charges. When the electrical potential difference becomes sufficiently large, lightning flashes, often followed by the thunder that results from the rapid expansion of air heated by the lightning bolt. Eventually, the weight of the condensed water and ice becomes too great for the updrafts to support, leading to heavy rainfall and sometimes hail as the storm dissipates. This entire process, from initial heating to final dissipation, is a testament to the rapid and localized energy transformations occurring within the atmospheric engine. On a larger scale, the El Niño Southern Oscillation, or ESO, phenomenon provides a compelling example of the powerful coupling between the ocean and atmosphere. ESO is a periodic fluctuation in sea surface temperatures and atmospheric pressure across the equatorial Pacific Ocean. During an El Niño event, the central and eastern equatorial Pacific experiences abnormally warm sea surface temperatures. This warming weakens the easterly trade winds, allowing the warm water to spread eastward. The shift in warm water distribution alters atmospheric convection patterns, leading to changes in rainfall and temperature across vast regions of the globe. For instance, El Niño often brings increased rainfall to parts of South America and the southern United States, while causing droughts in Southeast Asia and Australia. Conversely, La Niña, the cold phase of ENSO, is characterized by cooler than average sea surface temperatures in the equatorial Pacific, leading to a strengthening of the trade winds and often opposite weather impacts compared to El Niño. These large-scale oscillations demonstrate how seemingly distant oceanic conditions can have profound and far-reaching consequences for global weather patterns, affecting agriculture, water resources, and even the frequency and intensity of extreme weather events. The study of weather and climate is not merely an academic exercise, it has profound practical implications for human societies. Accurate weather forecasting is crucial for a myriad of activities, from agriculture and transportation to disaster preparedness and resource management. Farmers rely on forecasts to decide when to plant, irrigate, and harvest. Airlines use weather information to plan flight paths and ensure passenger safety. Emergency services depend on timely warnings of severe weather events like hurricanes, tornadoes, and blizzards to evacuate populations and mobilize resources. Predicting longer-term climate trends is equally vital for planning infrastructure development, managing water supplies, and developing strategies for adapting to and mitigating the impacts of climate change. The increasing frequency and intensity of extreme weather events such as heat waves, droughts, floods, and wildfires underscore the urgent need for a deeper understanding of Earth's atmospheric engine and its vulnerabilities, the complexity of Earth's weather systems makes accurate prediction a formidable challenge. The atmosphere is a chaotic system, meaning that small initial uncertainties can amplify rapidly, leading to significant divergence in forecasts over time. This is often referred to as the butterfly effect, where a butterfly flapping its wings in Brazil could theoretically contribute to a hurricane in Texas weeks later. While this is an oversimplification, it highlights the inherent sensitivity of atmospheric dynamics. Meteorologists employ sophisticated numerical weather prediction models, which are complex computer programs that simulate the behavior of the atmosphere based on physical laws. These models ingest vast amounts of observational data from satellites, weather balloons, radar, and ground stations, and then use powerful supercomputers to project future atmospheric states. Despite continuous advancements in computing power and modeling techniques, there remains an inherent limit to predictability, especially for long-range forecasts. Looking beyond the immediate weather, the Earth's climate system represents an even grander and more intricate tapestry of interconnected processes. Climate is essentially the long-term average of weather patterns in a particular region, encompassing not just temperature and precipitation, but also humidity, wind patterns, and the frequency of extreme events. The climate system involves not only the atmosphere and oceans, but also the cryosphere, ice and snow, the lithosphere, land surface, and the biosphere, living organisms. Each of these components interacts with and influences the others in complex ways, creating feedback loops that can either amplify or dampen climate change. For example, melting ice sheets reduce the Earth's albedo reflectivity, leading to more solar energy absorption and further warming, a positive feedback loop. Conversely, increased cloud cover due to warming could potentially reflect more sunlight, providing a negative feedback. Understanding these intricate feedback mechanisms is central to accurately projecting future climate scenarios. The history of Earth's climate is a story of constant change, punctuated by periods of both warming and cooling. Over geological timescales, natural factors such as variations in Earth's orbit around the Sun, Milankovitch cycles, volcanic eruptions, and changes in solar activity have driven significant climate shifts. However, the current period of rapid warming, unprecedented in its speed and magnitude, is overwhelmingly attributed to human activities, primarily the emission of greenhouse gases from the burning of fossil fuels, deforestation, and industrial processes. The scientific consensus on anthropogenic climate change is overwhelming, based on decades of rigorous research and observations from countless scientists worldwide. The consequences of this warming are already being observed globally, from rising sea levels and melting glaciers to more frequent and intense heat waves and altered precipitation patterns. The Earth's atmospheric engine is a powerful testament to the elegance and complexity of natural systems. It is a system in constant motion, driven by the sun's energy, shaped by the Earth's rotation, and modulated by the intricate interplay of gases, liquids, and solids. Every breath we take, every drop of water we drink, and every harvest we reap is ultimately connected to the efficient and delicate functioning of this planetary machinery. As we continue to grapple with the challenges of a changing climate, a deeper appreciation and understanding of how weather works becomes not just an intellectual pursuit, but an imperative for the sustainable future of our planet and all its inhabitants. The grand, intricate symphony of atmospheric and oceanic processes continues to unfold, a ceaseless reminder of the dynamic and living nature of our world. Each cloud that drifts across the sky, every ripple on the ocean's surface, and the very air we breathe are all manifestations of this ceaseless global effort to maintain an energy balance, a delicate equilibrium that underpins all life.